Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for word search 2 problem. Let's look at the problem description. We are given an m by n board of characters and a list of strings, words, and we have to return all the words that are present in this board. And there is a condition for constructing the words. So each word must be constructed from the letters of sequentially adjacent cells horizontally and vertically neighboring. The same cell may not be used more than once in a word. Let's take a look at the example 1. So here we have the 4x4 board of characters and the words list has 4 words: oath, pea, eat, rain. So among these 4 words we see the word eat. All the letters are horizontally neighboring, and then oath, A is neighboring to the letter O horizontally, and the rest of the letters are neighboring vertically. That's why the output has the words eat and oath. And in the case of example 2, the input word have A, B, C, B. Okay, so A, B, and C is located diagonally. So this is not a valid neighbor to B. So that's why the output is empty. So the constraints for this problem are, so m is the number of rows and n is the number of columns. The value for the m and n are ranging from 1 to 12. And each cell in the board has only the lowercase English letter. The length of the input words list is ranging from 1 to 30,000. And the individual word length is ranging from 1 to 10. Okay. And the input word also have only lowercase English letters. And also all the strings in the input word are unique. Let's look at the approach to solve this problem. We are given a 4x4 board and input words list which has 3 words in it. Among these 3 words, the first 2 words are present in the board. So A, N, T. So the output list will have the 2 words an, and ant. As per the problem description, we can construct the word from this board using the letters which are horizontally neighboring and vertically neighboring. In order to construct a word, we have to traverse the neighbors of the individual cells. For example, if we are in the cell T, then we have to choose one of the 4 letters A, H, E. Okay. So likewise, for each cell, the next possible cell will be one of the 4 neighboring cells. So we can traverse this board using recursion. For each neighbors, we can call a function to process that letters to check whether that matches with the input word or not. Okay. And before that, we need a try data structure to store this input words. Okay, so that the lookup will be easier. As we traverse the cell, we can pass the parent of that cell so that it will be easier to look up and check whether that word is valid word or not. Okay, so the first thing what we do is we build the try data structure for the words in the input words list. Okay, at the root there are 2 branches. Basically we have A, N and A, N, T, B, A, T. Basically the red node indicates that is the end of a valid word. Okay, here the word an ends, so that's why this node is red, and ant ends here, that's why this node is red. Bat ends here, that's why this node is red. In order to look up these words in this board, we start from the top left cell and traverse all the cells in this board recursively. Each iteration, we check whether the current cell's value matches with one of the child of the root node in the try data structure. Okay, for example, here the letter O, but the root do not have any children for the letter O. So we move to the next cell. Okay, and we see letter A, and when we look up whether there is a child in the root node with the letter A, there is one. So we initiate a recursive search from this cell. So from then on, for each letter we process, basically we have to pick up the horizontally neighboring cell or vertically neighboring cell. Next we pick up either letter T or M. Okay, and again we call the recursive function, and when we call the recursive function, now we pass the current node's parent. For example, this node will be passed to that called function, where we look up whether there is any child exist for the letter N in this node. So here there is a child node with the letter N. Each iteration we also check whether the current node has the end of word flag marked. Okay, in this case this is a valid word an, so this node is marked with true. So we combine all the letters so far we have traversed into a string and add it to the out list. So when we reach here, the an will be added to the out list. Next we pick up one of the neighbors of the letter N, which is A T. Okay, so in this case when we visit T, we check whether the node N has a child associated with value T. It does have one. So all the letters so far traversed will be combined into a string and then added to the out list. So now the output list have an and ant. So like that we traverse all the cells in the board and look up the try data structure and see whether the letters are matching. If they are matching, then we update the parent node and repeat that recursively until we reach the end of word. Basically for the lookup we use the try data structure. For traversal we are using recursion. That's what I have written here. So in the find words function, first we initialize the output list, then we build the try data structure with the input words list. Next we start traversing the cells in the board. Each iteration we check whether the root of the try has a child node that is associated with the current character. If that is true, then we add that letter to the slate. Basically we collect the letters traversed so far in the slate. Next we call the search function with the board and the try data structure and current row index and row column index and the slate and the output list as an argument to initiate the search. This function gets called recursively. Okay. So once all the cells are traversed, then finally we return the output list. So in the search function, we first assign the current character in the temporary variable, and then we check whether the current node has the end of word flag set. If this is set, then we convert the slate into a string and then add it to the output list, and we mark that end of word flag to false. Okay, so that this will not get added multiple times. Okay, and next we mark the current cell as visited, because one of the requirement is we cannot use the same cell again when we constitute a word. Okay, so that's why whenever we visit a cell we mark that cell in that search path. But when we come back after completing the search, then when we come back we have to restore that value, because when we look up the next word we need this value. Okay, after marking the cell as visited, we traverse all the 4 neighbors if they are in a valid boundary. Then we check whether the current node has a child node that is associated with the next possible letter, that is the neighbor cell's value. Okay, if that is true, then we add that neighbor cell's value to the slate, and then we call the recursive function with board, try, and the neighbors row index, neighbors column index, and slate and the output list. And we do this recursively until the word matches or none of the neighbor cell matches, then we return from here. And finally, the output list will have the list of words which are present in the board. Let's look at the flowchart. The input for the find words procedure is the board and then the input words list. Okay. First we initialize the out list and then the rows and columns variable. So the out list is initialized with empty list and the rows is initialized with the number of rows in the board and the column is initialized with number of columns in the board. Okay. Next we build the try data structure with the words in the input word list. Okay. Then we start traverse the cells in the input board. Okay. So each iteration we initialize the letter variable with the current cell's value. Next we check the root node whether it has any child node that is associated with this letter. If there is one, then we add that letter to the slate and then we call the search and add function to initiate the search. Otherwise we go ahead and process the next cell. Okay. So basically whenever there is a match, the first character in the word matches the one of the child node in the root node, then we initiate the search by calling the search and add functions. Okay. We repeat this until we process all the cells in the board and finally we return the out list. Next we look at the flowchart for the search and add function. The input for this search and add procedure is the board and the try data structure and the index of the current cell and the parent node and the slate and the out list. Okay. First we initialize the rows and columns and then the letter variable. So the rows and columns are initialized with number of rows and columns of the board and then the letter is initialized with the character at the index I and j. Then we look up the try data structure in the parent node for the child node which has the letter associated with it. Okay. So basically we look up the try data structure and get the child node's pointer, and if that child node has the end of word flag set to true, that means we found the word in the board. So first we mark that end of word flag to false and then convert the slate into a string and add it to the out list. If the end of word flag is not true, then save the current character. Next we then mark the cell as visited. This is to prevent the reuse of this cell when the current word is being searched. Next we check whether we processed all the neighbor cells of the cell at index I and j. Okay, that's what this for loop is doing. If all the neighbor cells are not processed, then we go ahead and initialize the next letter variable with the value of the current neighbor and then we check whether the current node has a child with the next letter. Okay. If that is the case, then the next letter is also matching with the current word. So we go ahead and add that next letter to the slate and then we call the search and add function recursively to look for the next letter in the word. Okay. Otherwise we go ahead and process the next neighbor. We repeat this and then finally when we after processing all the 4 neighbors, then we restore the value in the cell at index I and j with the original value before we call these recursive functions. So basically the search and add function called recursively to check whether there is a match for the characters in the input word. Let's move on to coding. First I define a structure for the node in the try data structure. So the structure have a children of type map of byte to pointer to a nodes and then end of word flag of type boolean. Next I implement the find words function. First I initialize the out list with empty list of string and then I initialize the rows and columns with the number of rows and number of columns of the board. Next I build the try data structure by calling build try function. Next I traverse the cells in the board. Each iteration I save the current cell's value in the letter variable. And then I look up the try data structures root node to check whether there is any child node for this letter. If OK is true, then I initialize the slate with the letter. And then I call the search and add function with board and the index of the current cell and the try data structure and the slate and then the address of the out list. Then I finally return the out list. Next I am going to implement the build try function. I have explained try data structures in another video in detail. I added the link in the description. Please check that video. So I'm going to skip explaining this function implementation. Next I implement the search and add function. First I initialize the rows and columns variable with the number of rows and columns of the board. And then I initialize the letter variable with the current cell's value. Next I look up the parent node's children's map for the child which has the value letter. Then I check whether that child has end of word flag set to true. If that is true, then I convert the slate into a string and add it to the out list. And then reset that end of word flag to false. Next I mark the current cell as visited. I define a constant visited with value 1. Next I define a distance list, which is a list of integer list that has an offset between the current cell and its neighbors. So this is the top cell and this is for the bottom cell and this is for the previous cell and this is for the next cell. Next I write the for loop to traverse this distance list. Each iteration I compute the index of the neighbor and check whether that index is in bound. If it is out of bound, then I will continue. Next I initialize the next letter variable with the value in the neighbor's cell. Then I look up the current node's children map for the child which has the next letter associated with it. If there is one, then I call the search and add function to process the next characters in the word. After coming out of the loop, I restore the value at the current cell with its original value. Next I'm going to run the test cases. All the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. We are given the 4x4 size board and the input words with 3 words an, ant and bat. Among these 3 words, an and ant are present in this board, an and ant. So the expected output has 2 words, an and ant. Okay. So first we initialize the out list to empty list. Okay. And then we initialize the rows and columns, and then we build the try data structure. We add these 3 words to the try data structure. Next we start traversing the cells in the input board, and each iteration we save the current cell's value in the variable letter. So in the iteration outer loop iteration 0 and the inner loop iteration 0, we read this cell and assign that in the variable letter. And then we look up whether there is any child node for the letter O, but there is no child with the with the value O. Okay, so we go ahead and process the next cell. So in the inner loop iteration 1, we pick up the letter A and we check whether there is a child with letter A in the try root node. There is one. Okay, so we add that letter A to the slate. So that's why the slate has the letter A. Then we call the search and add function recursively with the current cell's index and the board and try and slate and out list. Okay, the frame 1 is created. We enter this function. Here first we initialize the rows and columns and initialize the letter variable with the current cell's value. So the letter has A and the parent node is the root. Okay, and the rows and columns are initialized with 4. First we check whether there is a child for the letter in the current parent. So the current parent is root. So we check whether there is a child. There is one. So we check whether that node has the end of word flag set to true, but in this case it is not. So we go ahead and mark the current cell as visited. So the current cell is marked as visited. And next we have to check whether any of the neighbors are matching the next characters in the word. Next we have to find the character which is present in the current node's children list. Okay, so in this case we have only 3 valid neighbors. The top one is out of bound, so we are not going to visit that. So that's what this condition is. Then for each neighbors we initialize the next letters variable, and so this is the loop. So I directly go to this cell which matches the next letter. So in the for loop, in this for loop iteration 3, we have next index as 0 and the next row index is 0 and next column index is 2. Okay, and then we pick up the letter N and assign that to the next letter variable, and then we add it to the slate only if the next letter is the child of the current parent node. So in this case the parent node is this, so which has the child N. So that's why it gets added to the slate at the time of making the recursive call. So we call the search and add function only when the neighbor's next letter matches with one of the child of the current node. Okay, so we pass that current node as the parent of the next level search, and we append the next letter to the slate and we call the function again. So the frame 2 is created. So here we check whether the child node's end of word flag is marked. In this case it is marked because the AN is the valid word. So this node is marked with end of flag true. So we go ahead and added that word AN to the out list. And then we pick up one of the 4 neighbors T and check whether that neighbor matches with any of the child of the current node. So in this case there is one child with the value T. So we add that to the slate and then we make another recursive call. When we reach here, we check whether this node has the end of word flag set to true. So we convert this into a string and add it to the out list. So now the out list have 2 words, an and ant. And then after traversing all other nodes, finally we comes back to the find words function where the out list has 2 words, an and ant. That is an expected output. Next I'm going to do the time and space complexity analysis for this solution. The time complexity of this procedure is order of m times n 3 to the power k minus 1. Okay, where m is the number of rows, n is the number of columns, and k is the average length of the word in the input word list. Okay, basically we need to traverse all the cells. For example, the worst case scenario, if all the cells in the board matches the first letter in the input word, then we have to initiate the search in all the cells. That's why we have m times n times. This is for the recursion, how many cells we will be exploring in the entire search. Basically this many number of cells we ended up accessing when we do traverse the board. But whenever there is a match, the very first attempt we have 4 neighboring cells. For example, in this case, when this letter matches the first character of the words, we have 4 possible neighbors. But after processing, we move to the second letter. In this case, we have only these 3 options because we mark this as already visited, right? So likewise, for the rest of the traversal, we have only 3 possible next characters. So that's why it is 3. So basically for each level we go, total number of cells visited will increase by 3. Okay, so because the average length of the word is k, we have 3 to the power k minus 1 cells processed times m times n for the worst case where all the cells have the character that matches the first letter of the input word. Okay, so that's why the time complexity is order of m times n times 3 to the power k minus 1. Space complexity is order of k times n, where n is the average length of the word and k is the number of words in the input words list. Okay, basically we need to store all these words in the trie data structure. If they're all unique, then it will be the sum of all the words in the input word list, which is equal to the number of words times the average length of the word. For this case, first word length is 3, second is 3, and third and fourth is 6. The total length is 18, which is approximately 4 times 4. 4 is the number of words and 4 is the average length of the word. Okay. In addition to that, we need to allocate a space for the slate which carry the traversed cells value. Okay. Worst case, we will be having the slate of size which is equal to the longest word in the input word list. That's why this is 6. So the total space required is n times k plus n. We take the dominant term. That's why the space complexity is order of n times k. Thanks for watching this video. Have a great day.